Right now, at this very moment, you are floating through space at tremendous speed. You're traveling at roughly 220 kilometers per second around the center of our galaxy, which itself is hurtling through the cosmic void at over 600 kilometers per second. Yet you feel perfectly still, perfectly grounded, perfectly safe. This paradox, the profound mystery hidden in the ordinary, captures the essence of cosmology itself. Welcome to Sleep About Science. I'm your sleepy scientist, and tonight we're exploring 100 things that cosmology still can't explain. And if you drift off to sleep while listening, that's perfectly wonderful. In fact, there's something rather poetic about falling asleep while contemplating the universe's greatest mysteries. Before we begin, please make yourself comfortable wherever you are in the world. Pull up that blanket, adjust your pillow, and let yourself settle in. Remember, this is educational content, not medical advice. If you haven't subscribed yet, you might want to, so you never miss these gentle journeys into the cosmos and beyond. Now let's begin with a simple truth that will shape everything we discuss tonight. The more we learn about the universe, the more mysterious it becomes. Each answer we discover reveals 10 new questions we never knew to ask. It's as if the cosmos is an infinite library, and we've barely learned to read the first few letters of its alphabet. Consider this. We can see light that has traveled for over 13 billion years to reach us. Light that began its journey when the universe was just a cosmic infant. We can detect gravitational waves rippling through space-time itself. We can peer into the heart of black holes and watch galaxies dance across impossible distances. Yet for all our sophisticated instruments and elegant equations, the universe remains fundamentally mysterious. We understand perhaps 5% of what exists. The rest, Nisig, dark matter, dark energy, the very fabric of reality itself, remains hidden, waiting. Tonight we'll explore these mysteries together, not with frustration or urgency, but with the quiet wonder of children looking up at stars for the first time. Each mystery we encounter isn't a failure of science, but an invitation to marvel at how much more there is to discover. Let's start with something so fundamental that we rarely question it, the very existence of existence itself. Why does anything exist at all, rather than nothing? This question, which philosophers call the problem of being, strikes at the heart of cosmology. We can describe the Big Bang, map cosmic background radiation, and trace the evolution of matter and energy across billions of years. But we cannot explain why there should be a universe in the first place. The mathematical equations that govern reality are silent on their own existence. They describe what is, but not why there is anything for them to describe. This leads us to our second mystery, the nature of time itself. We experience time as flowing, as moving from past through present toward future, yet physics suggests time might be more like space mines, a dimension we can move through rather than a river that carries us along. Einstein showed us that time is relative, that it bends and stretches with gravity and motion, but we still don't understand why we remember the past and not the future, why cause seems to precede effect, why we feel time's arrow pointing in one direction through the cosmos. The third great mystery is consciousness itself, and its relationship to the cosmos. How does the universe become aware of itself through beings like us? Somehow, arrangements of atoms that formed in stellar furnaces billions of years ago have organized themselves into patterns that can contemplate their own existence. The carbon in your body, the iron in your blood, the calcium in your bones, all were forged in the hearts of dying stars. Yet through some process we don't understand, this stellar material has become capable of wonder, of love, of the very thoughts you're thinking right now as you listen to these words. But let's drift deeper into the cosmic mysteries, starting with the very first moment. What would he imagine was the first moment? The Big Bang Theory describes the universe expanding from an incredibly hot, dense state, roughly 13.8 billion years ago. But what caused this expansion to begin? What existed before the Big Bang? These questions lead us into territory where physics becomes poetry, where mathematics dissolves into pure speculation. Some theorists propose cyclic universes that expand and contract eternally. Others suggest our cosmos emerged from quantum fluctuations in a pre-existing void. Still others wonder if the question itself is meaningless, like asking what's north of the North Pole. The mystery deepens when we consider cosmic inflations, the idea that space itself underwent a period of exponential expansion in the universe's first fraction of a second. This theory elegantly explains many features of the cosmos we observe today, but it raises profound questions. What drove inflation to begin? What caused it to stop? And if inflation can happen once, why not countless times? creating an infinite multiverse of pocket universes, each with its own physical laws and constants. This brings us to the fine-tuning problem, one of cosmology's most puzzling features: the fundamental constants of nature. The strength of gravity, the mass of electrons, the rate of cosmic expansion, all seem precisely calibrated to allow complexity, chemistry, and ultimately life to emerge. Change any of these values by tiny amounts, and stars wouldn't form, atoms wouldn't hold together, or the universe would collapse before anything interesting could happen. Is this extraordinary precision the result of blind chance, conscious design, or natural selection among multiple universes? We simply don't know. Speaking of things we don't know, let's turn to dark matter, the invisible substance that apparently makes up about 27% of the universe. We know dark matter exists because we can see its gravitational effects. It holds galaxies together, bends light from distant objects, and shapes the largest structures in the cosmos. Yet dark matter particles don't interact with light or ordinary matter in ways we can directly detect. Decades of increasingly sophisticated experiments have failed to capture a single dark matter particle. It's as if the universe is filled with ghosts that we can perceive only by their shadows. Even more mysterious is dark energy, which comprises roughly 68% of everything that exists. In 1998, astronomers discovered that the expansion of the universe is accelerating. Space itself is stretching faster and faster, driven by some unknown force they named dark energy. We don't know what dark energy is, where it comes from, or why its strength seems perfectly calibrated to dominate the universe's evolution at this particular cosmic epoch. It's possible that dark energy isn't a thing at all, but rather a sign that our understanding of gravity itself is incomplete. The nature of black holes presents another cascade of mysteries. These objects are so dense that nothing, not even light, can escape their gravitational pull once it crosses the event horizon. But what happens to information that falls into a black hole? According to quantum mechanics, information cannot be destroyed, yet black holes seem to erase whatever falls into them completely. This information paradox suggests that either our understanding of quantum mechanics or our understanding of gravity, or so both, is fundamentally flawed. Stephen Hawking showed that black holes should slowly evaporate by emitting radiation, but this Hawking radiation appears to carry no information about what fell into the black hole. It's as if black holes are cosmic shredders that violate one of physics' most fundamental principles. Recent theoretical work suggests the information might be preserved in subtle correlations in the Hawking radiation, but proving this would require observations lasting longer than the age of the universe. At the heart of every black hole lies a gravitational singularity, a point where matter is compressed to infinite density and space-time curvature becomes infinite. But infinity appearing in physics usually signals that our theories have broken down. What really exists at the center of a black hole? Is it truly a mathematical point of infinite density, or does some unknown physics prevent the formation of true singularities? The mystery extends to the earliest moments of the Big Bang, when the entire observable universe was compressed to a size smaller than an atom. Our equations suggest this initial state was also a singularity, but this seems to violate everything we know about quantum mechanics. Surely at such tiny scales, quantum effects would prevent true singularities from forming, yet we lack a complete theory of quantum gravity to describe what actually happened. This absence of quantum gravity represents one of physics' greatest challenges. We have two supremely successful theories: general relativity, which describes gravity and large-scale structure, and quantum mechanics, which governs the microscopic world. But these theories make fundamentally incompatible assumptions about the nature of reality. Reconciling them would give us a theory of everything that could describe physics from the smallest scales to the largest. Despite decades of work on string theory, loop quantum gravity, and other approaches, this unified theory remains tantalizingly out of reach. The search for quantum gravity leads us to question the very nature of space and time. Are they continuous, like smooth sheets of rubber, or are they made of discrete, indivisible bits at the smallest scales? If space and time are quantized, made of tiny fundamental units, then the universe might be more like a cosmic computer, processing information in discrete steps. But if so, what is the universe computing? And who or what wrote the program? Some theorists propose that reality is fundamentally mathematical, that the universe doesn't just follow mathematical laws, but actually is a mathematical structure. In this view, consciousness and physical objects are simply different types of information processing patterns within an abstract mathematical framework. But why should mathematics correspond to reality at all? And why do some mathematical structures manifest as physical universes while others remain purely abstract? The question of mathematical reality connects to another deep mystery: the nature of physical laws themselves. Why do particles behave according to precise mathematical rules? Why is the universe comprehensible to minds like ours? The physicist Eugene Winger famously called this the unreasonable effectiveness of mathematics in the natural sciences. We can use abstract mathematical tools developed centuries ago to predict the behavior of subatomic particles, or the merger of black holes billions of light years away. This seems almost miraculous, yet we have no explanation for why it works. Consider the strange world of quantum mechanics, where particles can exist in multiple states simultaneously until observed, where distant particles can be instantaneously connected through quantum entanglement, and where the act of measurement seems to collapse infinite possibilities into single realities. Nearly a century after its development, we still debate what quantum mechanics actually means. Is reality fundamentally probabilistic, or are there hidden variables we haven't discovered? Do quantum measurements create reality, or simply reveal what already existed? Does consciousness play a special role in collapsing quantum states? The measurement problem in quantum mechanics connects to consciousness in puzzling ways. The equations of quantum mechanics perfectly describe what we observe in experiments, but they seem to require an observer to transform quantum probabilities into definite outcomes. Some interpretations suggest that consciousness itself is necessary to collapse quantum states, making mind fundamental to physical reality. Others propose that quantum states never actually collapse. Instead, reality splits into parallel branches for every possible outcome, creating an infinite multiverse of parallel worlds. Speaking of multiple universes, the multiverse concept has become increasingly prominent in cosmology, though it remains deeply controversial. If cosmic inflation is eternal, it might create an infinite number of pocket universes, each with different physical constants and laws. In this vast multiverse, every possible universe would exist somewhere. Our universe's apparent fine-tuning for life would simply be a selection effect. We observe a life-friendly universe, because we couldn't exist in any other type. But the multiverse hypothesis raises profound questions about the nature of scientific explanation. If anything that can happen does happen somewhere in the multiverse, then every observation is equally probable. How can we make predictions or test theories if all possibilities are realized? The multiverse might explain fine-tuning, but it seems to make science itself impossible by removing the concept of a unique testable reality. The nature of emergence presents another set of mysteries that span from quantum mechanics to cosmology. How do simple rules governing individual particles give rise to complex phenomena like chemistry, biology, consciousness, and love? The behavior of a single hydrogen atom is perfectly described by quantum mechanics, but somehow billions of such atoms can organize themselves into patterns that write poetry and contemplate the stars. This emergence of complexity from simplicity appears at every scale, from molecules to cells to ecosystems to galaxies. Yet we lack a general theory of how it works. At the largest scales, the universe itself shows emergent properties that puzzle cosmologists. Dark matter particles that barely interact with anything somehow organize themselves into vast webs of filaments spanning billions of light years. Galaxies form along these filaments like beads on cosmic strings, creating a structure that resembles a vast neural network. Is this similarity meaningful or simply a coincidence? Could the universe itself be a kind of cosmic brain, processing information through the flow of matter and energy across these galactic connections? The question of cosmic structure leads us to consider the universe's ultimate fate. Will expansion continue forever, spreading matter and energy ever thinner until the last stars burn out and black holes evaporate into the void? Will dark energy eventually overcome all other forces, ripping apart atoms themselves in a big rip, or might the expansion reverse, leading to a big crunch that mirrors the Big Bang in reverse? Each scenario raises profound questions about the nature of ending and beginning, infinity and finitude. But perhaps the most mysterious aspect of cosmology is how unlikely our existence seems. The universe began in an almost perfectly smooth state, with only tiny density fluctuations that eventually grew into stars and galaxies. If the initial smoothness had been perfect, no structures would have formed. If the fluctuations had been much larger, matter would have collapsed into black holes before stars could ignite. The balance seems impossibly precise, as if the universe was carefully tuned to produce complexity and consciousness. This cosmic fine-tuning extends to the formation of life itself. The universe had to exist long enough for heavy elements to form in stellar cores and spread through space. It needed the right type of stars, not too hot, not too cool, not too short-lived. Planets had to form at just the right distances from these stars, with just the right compositions and magnetic fields. The list of apparent coincidences required for life seems almost endless. Yet here we are, contemplating these mysteries from our small planet orbiting an ordinary star in an unremarkable galaxy. We are arrangements of atoms that became self-aware, patterns of matter and energy that can recognize beauty, feel wonder, and ask questions about existence itself. Through some process we don't understand, the universe has evolved beings capable of studying its own nature. We are the cosmos becoming conscious of itself, matter awakening to contemplate its own existence. This recognition leads to profound questions about the relationship between mind and reality. Is consciousness simply an emergent property of sufficiently complex information processing, or is it fundamental to the fabric of reality itself? Some theories suggest that consciousness is a basic feature of the universe, present at every level from electrons to galaxies. In this view, human awareness is just the most complex form we know of a universal property of matter and energy. The hard problem of consciousness, explaining how subjective experience arises from objective physical processes, remains one of the deepest mysteries in science. We can map neural activity, identify the brain regions involved in different mental functions, and even predict some thoughts from brain scans. But none of this explains why there is something it feels like to be conscious, why we have inner experiences at all, rather than simply behaving like sophisticated unconscious machines. This mystery becomes even deeper when we consider the possibility that consciousness might play a role in shaping physical reality through quantum mechanics. Some interpretations suggest that conscious observation is necessary to collapse quantum states into definite outcomes. If true, this would make mind not just an observer of the universe but an active participant in its creation. The universe might literally depend on consciousness to exist in definite form. But consciousness itself seems impossible to locate in space and time. Where in your brain is the experience of seeing blue or feeling curious or understanding these words? Neuroscience can identify neural correlates of consciousness, patterns of brain activity associated with different experiences, but it cannot find experience itself. Your subjective awareness seems to exist nowhere and everywhere simultaneously, like a field that encompasses all your thoughts and sensations without having a specific location. This distributed nature of consciousness resembles some features of quantum mechanics, where particles can exist in multiple locations simultaneously until measured. Some theorists propose that consciousness is a quantum phenomenon, arising from quantum processes in tiny structures within brain cells, but quantum effects seem too fragile to survive in the warm, noisy environment of the brain. The connection between consciousness and quantum mechanics remains speculative and controversial. The mystery deepens when we consider the possibility of other forms of consciousness in the universe. If consciousness is fundamental rather than emergent, it might manifest at scales we haven't considered. Could ecosystems be conscious? Planets, stars, galaxies. The idea seems far-fetched, but so did many scientific discoveries before they were accepted. We simply don't know enough about consciousness to rule out any possibilities. This uncertainty about consciousness connects to broader questions about life in the universe. Despite decades of searching, we have found no definitive evidence of life beyond Earth. The Fermi paradox asks why, given the vast number of stars and planets in the universe and the apparent ease with which life emerged on Earth, we haven't detected any signs of other civilizations. Where is everybody? Possible answers to the Fermi paradox range from the reassuring to the terrifying. Perhaps life is much rarer than we think, requiring an extremely unlikely series of coincidences. Perhaps intelligent life tends to destroy itself before developing the technology for interstellar communication. Perhaps advanced civilizations deliberately avoid contact with primitive species like us. Or perhaps we're looking for the wrong signs, failing to recognize forms of life and intelligence radically different from our own. The search for life elsewhere forces us to examine our assumptions about what life is and how it might manifest. Earth-based life relies on liquid water, carbon chemistry, and relatively narrow ranges of temperature and pressure. But could life exist in the ammonia oceans of Saturn's moon Titan, in the hydrogen atmosphere of Jupiter, in the vacuum of space itself? We're beginning to realize how limited our definition of life might be. Even more challenging is recognizing intelligence that evolved along completely different paths. We tend to look for signs of technology similar to our own minus radio signals, signs of industrial activity, massive engineering projects. But an intelligence that developed in the deep ocean might have no concept of fire or metallurgy. A collective intelligence spread across an entire planet might think and act on timescales that make our civilization seem like a brief flicker. We might be surrounded by intelligence we cannot recognize because it's nothing like our own. This problem of recognition extends to our understanding of reality itself. We perceive the universe through senses evolved to help our ancestors survive on Earth. Our eyes see a narrow slice of the electromagnetic spectrum. Our ears detect a limited range of vibrations. Our brains process information in ways shaped by millions of years of natural selection. How much of reality are we missing simply because we lack the right sensory equipment or conceptual frameworks to perceive it? The question becomes even more profound when we consider that our scientific instruments are ultimately extensions of human perception, designed and interpreted by minds with evolutionary limitations. Our telescopes show us light, but the universe is filled with phenomena that don't emit or reflect photons. Our particle accelerators probe matter by smashing things together, but reality might include forms of existence that don't respond to such violent interrogation. We're like beings trying to understand music while being completely deaf, inferring the existence of symphonies from the vibrations we feel through our feet. This limitation of human perception leads to one of cosmology's deepest questions. Is the universe inherently comprehensible, or are there aspects of reality that conscious minds can never understand? We've made remarkable progress in understanding everything from subatomic particles to galactic clusters, but perhaps we're approaching the limits of what minds like ours can grasp. There might be truths about existence that require forms of intelligence we cannot imagine, or that are simply beyond the reach of any conceivable form of consciousness. The possibility of cognitive limitations raises questions about the nature of scientific knowledge itself. Science works by creating models and theories that explain observations and make testable predictions, but models are not reality. They're simplified representations that capture some aspects of truth while necessarily ignoring others. Even our most successful theories, like quantum mechanics and general relativity, might be approximations to a deeper reality we cannot directly access. This leads us to consider the relationship between mathematics and physics. Mathematical structures seem to exist independently of the physical universe. The properties of circles and prime numbers would be the same whether or not any physical circles or countable objects existed. Yet these abstract mathematical relationships also seem to govern the behavior of every particle and wave in the cosmos. Why should the universe obey mathematical laws at all? Why should abstract, non-physical relationships have any connection to concrete physical reality? Some cosmologists propose that this connection exists because the universe itself is mathematical in nature, that physical objects are simply patterns of information, relationships, and mathematical structures. In this view, matter and energy are not the fundamental constituents of reality, but rather emergent features of underlying mathematical patterns. Space and time themselves might be approximations to more fundamental mathematical relationships that exist outside of space-time. But if reality is fundamentally mathematical, what determines which mathematical structures manifest as physical universes? Is there some deeper principle that selects certain equations to become real while leaving others as pure abstractions? Or do all possible mathematical structures exist somewhere, with consciousness emerging only in those complex enough to support self-aware patterns of information processing? These questions blur the boundary between physics and philosophy, between what we can observe and what we can only speculate about. They remind us that cosmology is not just about mapping the universe, but about understanding our place within it, not just as observers, but as participants in the cosmic story. As we drift deeper into these mysteries, it's worth pausing to appreciate how remarkable it is that we can even ask such questions. 4 billion years ago, Earth was a sterile rock circling a young star. Through processes we're still trying to understand, simple chemicals organized themselves into patterns capable of reproduction and evolution. Over vast stretches of time, these patterns became increasingly complex, eventually developing the ability to sense their environment, to remember, to learn, and ultimately to wonder about their own existence. Now, after billions of years of evolution, matter has arranged itself into forms capable of detecting gravitational waves, mapping dark matter, and pondering the nature of consciousness itself. The atoms in your body, forged in stellar cores, have become capable of contemplating the very stars that created them. Carbon, nitrogen, oxygen, and other elements have somehow organized themselves into patterns that can experience awe, love, curiosity, and the profound mystery of being alive in an uncertain universe. This emergence of consciousness from matter remains one of the deepest mysteries in cosmology. How does information processing become subjective experience? How do neural patterns become thoughts and feelings? Why should there be anything it feels like to be a conscious being rather than just unconscious information processing? The gap between objective physical processes and subjective experience seems unbridgeable, yet here we are, bridging it simply by being aware. The mystery becomes even deeper when we consider that consciousness seems to be the only way the universe can know itself. Stars burn and planets orbit, galaxies collide and black holes merge, but none of these cosmic events mean anything without conscious observers to witness and understand them. Through beings like us, the universe becomes self-aware. We are the cosmos waking up to contemplate its own nature. But this awakening reveals how little we actually understand. Despite centuries of scientific progress, the universe remains fundamentally mysterious. We know that it exists, that it's approximately 13.8 billion years old, that it's expanding and cooling, that it's filled mostly with unknown forms of matter and energy. But we don't know why it exists, what it's expanding into, what dark matter and dark energy actually are, or whether consciousness is a cosmic accident or a fundamental feature of reality. These mysteries remind us that science is not about certainty, but about the ongoing refinement of uncertainty. Each discovery doesn't just answer questions, it reveals new depths of mystery we never knew existed. The universe is not a puzzle to be solved, but an infinite source of wonder to be explored. Every answer opens new questions, every explanation reveals new phenomena that need explaining. This endless unfolding of mystery is not a failure of science, but its greatest triumph. It means the universe is far stranger and more wonderful than we ever imagined. It means there will always be new frontiers to explore, new questions to ask, new forms of beauty to discover. The fact that cosmology still can't explain so much about the universe is not a limitation misses. It's an invitation to keep wondering, keep exploring, keep marveling at the extraordinary reality in which we find ourselves. As we near the end of our journey through cosmology's greatest mysteries tonight, it's worth reflecting on what these unknowns tell us about our place in the cosmos. We are not separate from the universe we study. We are part of it, expressions of its complexity and creativity. The same physical laws that govern distant galaxies also govern the thoughts you're thinking right now. The same quantum processes that occurred in the first moments after the Big Bang are occurring in your brain as you process these words. You are made of star stuff contemplating star stuff. You are the universe becoming conscious of itself through billions of years of cosmic evolution. Every question you ask about existence is the cosmos questioning its own nature. Every moment of wonder you experience is the universe marveling at its own mystery and beauty. This perspective doesn't diminish the mystery, that it deepens it. How extraordinary that unconscious matter and energy should have organized itself into forms capable of love, art, science, and philosophy. How remarkable that the universe has evolved beings capable of detecting its cosmic microwave background radiation, mapping its large-scale structure, and pondering the nature of space and time themselves. We began tonight by noting that the more we learn about the universe, the more mysterious it becomes. This is not a paradox to be solved, but a truth to be celebrated. It means reality is far richer and more beautiful than any story we could invent. It means there are always new wonders waiting to be discovered, new forms of beauty to be appreciated, new reasons to feel awe at the extraordinary cosmos in which we live. The 100 mysteries we've explored tonight, from the nature of time and consciousness to dark matter and quantum gravity, are not obstacles to understanding. They're invitations to wonder, reasons to feel grateful that we live in such an extraordinary universe, reminders that existence itself is the most remarkable and mysterious fact we know. As you rest tonight, wherever you are in the world, remember that you are floating through space on a planet orbiting a star in a galaxy filled with hundreds of billions of other stars, in a universe that contains trillions of other galaxies, all expanding through space-time in ways we're still trying to understand. You are participating in the most extraordinary story ever told, the story of how the universe became conscious of itself through beings capable of love, wonder, and the courage to ask questions about existence itself. Sleep well, knowing that you are part of the greatest mystery of all, the mystery of conscious beings capable of contemplating their own cosmic nature. Dream of dark matter dancing through space, of quantum particles existing in multiple states simultaneously, of black holes warping space-time itself. Dream of the universe awakening to its own beauty through minds like yours. And remember, every night as you close your eyes, you're participating in one of the cosmos' most beautiful mysteries, the daily cycle of consciousness emerging from and returning to the quantum realm of possibilities from which all experience springs. Thank you for joining me tonight on this journey through cosmology's greatest unknowns. Thank you for bringing your wonderful, mysterious consciousness to bear on these questions that have puzzled minds for centuries. Thank you for being part of the universe's ongoing quest to understand itself. Wherever you are listening tonight, whatever time zone you're in, whatever questions keep you awake with wonder, know that you're not alone. We're all fellow travelers in this extraordinary cosmos, all participants in the greatest adventure story ever told. The story of how matter became mind, how simplicity became complexity, how the universe learned to ask questions about its own existence. Sweet dreams, and may your rest be filled with the quiet wonder of knowing that you are, quite literally, made of stars contemplating the cosmos from which they came. Good night, fellow cosmic wanderers. Sleep about science and wake up tomorrow ready to marvel once again at the beautiful mysteries that surround us. But there are so many more mysteries we haven't even touched upon tonight. Consider the nature of virtual particle Mons fluctuations that pop in and out of existence in the vacuum of space. These ghostly particles seem to violate the conservation of energy, borrowing energy from the universe's quantum credit system and paying it back so quickly that the universe's bookkeeping can't quite keep track. Yet these virtual particles have real effects. They contribute to the Casimir force, influence the behavior of atoms, and might even be responsible for Hawking radiation from black holes. The vacuum itself is mysterious. What we call empty space isn't empty at all, but seething with quantum activity. Virtual particles appear and disappear, electromagnetic fields fluctuate, and energy density varies from point to point. This quantum vacuum might contain more energy than all the matter in the observable universe, yet we can't access it directly. Some theories suggest that the vacuum energy might be responsible for dark energy, but the calculations give answers that are wrong by more than 120 orders of magnitude. The worst prediction in the history of physics. Speaking of wrong predictions, let's consider the hierarchy problem. The Higgs boson, discovered in 2012, gives mass to other particles through the Higgs field that permeates all of space. But quantum corrections should make the Higgs field so energetic that it would tear the universe apart. The fact that this doesn't happen suggests that there's some unknown physics that precisely cancels out these corrections to an accuracy of 1 part in 10 circumflex 16. This level of fine-tuning seems almost impossible unless there's some deeper principle we haven't discovered. The strong CP problem presents another puzzle of extraordinary fine-tuning. The strong nuclear force could, in principle, violate charge parity symmetry in ways that would make neutrons have electric dipole moments. Experiments show that if neutrons have such moments, they're smaller than we can measure by many orders of magnitude. This suggests that a fundamental parameter in the theory of the strong force is fine-tuned to be extraordinarily close to zero. We have no explanation for this fine-tuning, though some theories propose the existence of new particles called axions to solve the problem. Axions, if they exist, would be among the most mysterious particles in the universe. They would interact so weakly with ordinary matter that trillions of them could pass through your body every second without you noticing. Yet they might make up some or all of dark matter. Experiments around the world are searching for these ghostly particles by looking for their faint interactions with magnetic fields. If found, axions would solve multiple mysteries simultaneously, explaining dark matter, the strong CP problem, and potentially providing insights into the earliest moments of the universe. But axions are just one candidate for dark matter. Other possibilities include sterile neutrinos, primordial black holes, and exotic particles with names like WIMPs and WIMPzillas. Each candidate implies a different story about how the universe evolved, different predictions about what we might observe, and different possibilities for the ultimate fate of reality itself. The identity of dark matter might determine whether the universe ends in heat death, Big Rip, or Big Crunch. The neutrinos we do know about present their own mysteries. These ghostly particles are produced by nuclear reactions in the sun, by cosmic ray interactions in the atmosphere, and by radioactive decay in the Earth. Trillions of neutrinos pass through your body every second, but they interact so weakly with matter that they could travel through light years of lid without hitting a single atom. Detecting them requires massive underground laboratories filled with thousands of tons of carefully monitored material. What makes neutrinos especially mysterious is that they have mass, but we don't know why. In the standard model of particle physics, neutrinos should be massless, like photons. The discovery that they oscillate between different types proves they have mass, but this mass is extraordinarily small, millions of times lighter than electrons. We don't understand why neutrino masses are so different from all other particle masses, or what mechanism gives them mass in the first place. The pattern of particle masses more generally is one of physics' great mysteries. Why is the electron 207 times lighter than the muon, which is itself 9 times lighter than the tar? Why is the top quark almost 200 times heavier than the proton? These mass ratios seem arbitrary, with no obvious pattern or underlying principle. The Higgs mechanism explains how particles get mass, but not why they get the specific masses they do. The Standard Model itself, despite its extraordinary success in explaining particle interactions, leaves many questions unanswered. Why are there 3 generations of particles when one would seem sufficient for building atoms? Why are there 4 fundamental forces rather than 3 or 5? Why do the strengths of these forces have the specific values they do? The Standard Model is clearly incomplete, but we don't know what lies beyond it. One tantalizing clue comes from the apparent unification of forces at high energies. At low energies, the electromagnetic and weak nuclear forces seem completely different, but at energies characteristic of the early universe, they merge into a single electroweak force. Similarly, some theories suggest that at even higher energies, the strong force might unify with the electroweak force into a single grand unified force. At the highest energies of all, near the Planck scale, gravity itself might unify with the other forces into a single theory of everything. But this grand unification program faces serious challenges. Most grand unified theories predict that protons should decay, but experiments have found no evidence of proton decay despite decades of searching. The theories also predict the existence of magnetic monopoles, Midas particles that carry isolated north or south magnetic poles, Midas, but none have ever been found. The unification might work mathematically, but nature seems reluctant to cooperate with our elegant theoretical constructions. String theory represents perhaps the most ambitious attempt to unify all forces and particles into a single theoretical framework. In string theory, the fundamental constituents of reality are not point particles but tiny vibrating strings. Different vibrational modes of these strings correspond to different particles, like different notes on a cosmic guitar. The theory naturally includes gravity and seems to solve many problems that plague other approaches to quantum gravity. But string theory has its own mysteries and challenges. The theory only works consistently in 10 or 11 dimensions, far more than the 4 dimensions of spacetime we observe. The extra dimensions must be compactified, curled up so small that we can't detect them. But there are an enormous number of ways to compactify extra dimensions, each giving rise to different physics in our 4-dimensional world. This landscape of possible string theories might contain 10 circumflex 500 or more different possibilities, making it impossible to determine which one describes our universe. The string theory landscape connects to questions about the multiverse. If all possible compactifications exist somewhere, then our universe's particular properties, its physical constants, its spatial dimensions, its laws of physics, would be just one possibility among countless others. This would explain fine-tuning through what physicists call the anthropic principle. We observe a universe suitable for life simply because we couldn't exist in any other type. But the anthropic principle is deeply controversial. Many physicists argue that it abandons the goal of explaining why the universe has the properties it does, replacing explanation with the claim that all possibilities exist somewhere. It seems to make physics unscientific by removing the possibility of unique testable predictions. Others argue that the anthropic principle is simply a recognition that our observations are necessarily biased toward universes compatible with our existence. The anthropic principle becomes especially puzzling when applied to the arrow of time. The second law of thermodynamics tells us that entropy μ, roughly, disorder μ increases over time. This gives time a direction. We remember the past but not the future. Eggs break but don't spontaneously reassemble. Heat flows from hot objects to cold ones but not the reverse. But the fundamental laws of physics are largely time-symmetric. They work equally well forward or backward in time. The arrow of time seems to arise from initial conditions. The early universe was in an extraordinarily low entropy state, Midas very smooth and uniform. As the universe evolved, gravitational clumping increased entropy, creating the complex structures we see today. But why did the universe begin in such a special low entropy state? This seems to require fine-tuning that's even more extreme than the fine-tuning of physical constants. Some cosmologists propose that the arrow of time emerges naturally from the multiverse. In an eternally inflating cosmos, pocket universes are constantly being created. Most of these universes would be in high-entropy, chaotic states. But occasionally, quantum fluctuations would create a pocket universe in a low-entropy state, giving it a well-defined arrow of time. We observe such a universe simply because observers can only exist in universes with clear temporal direction. But this explanation raises new questions about the nature of probability and observation in an infinite multiverse. If every possible universe exists somewhere, how do we calculate the probability of any particular observation? Standard probability theory breaks down when dealing with infinite sets. The measure problem in cosmology means how to assign probabilities to different outcomes in an infinite multiverse remains unsolved. These foundational questions about probability and observation connect to deeper mysteries about the nature of scientific knowledge itself. Science works by making predictions that can be tested through observation and experiment, but in an infinite multiverse where everything happens somewhere, every observation is equally probable. How can we maintain scientific methodology when all possibilities are realized? The measurement problem in quantum mechanics presents similar challenges. Quantum theory tells us that particles exist in superpositions of multiple states until measured, but the theory doesn't explain what constitutes a measurement or why measurements produce definite outcomes from quantum probabilities. The Copenhagen interpretation simply asserts that measurement collapses the wave function, but this seems to introduce classical concepts into an otherwise quantum framework. Alternative interpretations of quantum mechanics each have their own mysteries. The many worlds interpretation suggests that measurement doesn't collapse the wave function, but rather splits reality into multiple branches, one for each possible outcome. This eliminates the measurement problem but introduces a new mystery. If all possible outcomes happen, why do we experience only one branch of reality, and what determines which branch our consciousness follows? Hidden variable theories propose that quantum randomness reflects our ignorance of underlying deterministic processes, but Bell's theorem shows that any hidden variable theory must be non-local mine, allowing instantaneous influences between distant particles. This seems to violate relativity's prohibition on faster-than-light communication. Experiments confirming Bell inequality violations suggest that either locality or realism, the idea that particles have definite properties independent of observation, must be abandoned. The delayed choice quantum eraser experiment presents even stranger puzzles. These experiments seem to show that measurements performed in the future can retroactively determine the past behavior of particles. A photon's path through a double-slit apparatus can be determined by measurements made after the photon has already been detected. This suggests that causality itself might be more complex than we assumed, with future events influencing past states in ways that don't permit communication, but do seem to violate our intuitions about time and causation. Quantum entanglement, which Einstein called spooky action at a distance, remains one of the most mysterious features of reality. When two particles become entangled, measuring one instantly affects the other, regardless of the distance between them. This correlation is stronger than any classical physics can explain, yet it doesn't allow faster-than-light communication. Somehow, entangled particles maintain mysterious connections that transcend space and time, while respecting the limitations imposed by relativity. Recent experiments have demonstrated entanglement between particles separated by hundreds of kilometers, confirmed that the correlations occur faster than light could travel between the particles, and shown that the entanglement persists even when measurements are made in space-like separated regions of space-time. These results confirm quantum mechanics' strangest predictions while deepening the mystery of how such correlations are possible. The puzzle deepens when we consider that entanglement might be fundamental to the structure of space-time itself. Some theories suggest that the geometry of space emerges from patterns of quantum entanglement between microscopic degrees of freedom. In this view, distance and spatial relationships are not fundamental features of reality, but rather emergent properties of underlying quantum connections. Space itself might be woven from entanglement. This idea connects to the holographic principle, one of the most surprising discoveries in theoretical physics. The principle suggests that all the information contained in a volume of space can be encoded on its two-dimensional boundary, like a hologram that encodes three-dimensional images on a flat surface. This seems to violate our intuitions about the relationship between volume and surface area, yet it emerges naturally from studies of black hole thermodynamics. The holographic principle suggests that reality itself might be holographic. The three-dimensional world we experience might be a projection of information encoded on a distant two-dimensional surface. This would mean that depth might see the third spatial dimension is somehow illusory, emerging from more fundamental two-dimensional processes. It's as if we're living inside a cosmic hologram without realizing it. But if reality is holographic, what exists on the boundary where information is actually stored, And why do we experience a three-dimensional projection rather than the two-dimensional reality? The holographic principle raises profound questions about the nature of existence, observation, and the relationship between information and physical reality. Information itself presents deep mysteries in cosmology. The bit, Nethidine, the fundamental unit of information, seems to play a role as basic as matter and energy in determining the universe's structure and evolution. John Wheeler proposed that reality is fundamentally informational, captured in his phrase "it from bit." In this view, matter and energy are secondary phenomena that emerge from more fundamental informational processes. But what is information in the absence of minds to process it? Classical information seems to require conscious observers to give it meaning. Yet quantum information appears to exist independently of observation, encoded in the correlations between particles and fields. The universe seems to be processing information constantly, even in regions where no conscious observers exist. This suggests that information processing might be a fundamental feature of reality, independent of consciousness. The connection between information and consciousness remains mysterious. Integrated information theory proposes that consciousness corresponds to integrated information processing, the degree to which a system's parts work together to process information in ways that cannot be reduced to simpler components. This would make consciousness a measurable quantity that could exist at many levels, from simple thermostats to human brains to potentially vast cosmic structures. But IIT faces serious challenges. It seems to predict that simple systems like photodiodes can be conscious, and that human consciousness might be less integrated than the consciousness of certain simple networks. The theory also struggles with the boundary problem, determining where one conscious system ends and another begins in a universe where everything is connected through physical interactions. The hard problem of consciousness, explaining why subjective experience exists at all, remains unsolved. We can explain the functional aspects of consciousness, how brains process information, recognize patterns, form memories, and control behavior. But none of these explanations address why there should be something it feels like to perform these functions. Why isn't the brain simply an unconscious information processor, responding to inputs and producing outputs without any inner experience? Some philosophers argue that consciousness is fundamental to reality, like mass or electric charge. In this view, conscious experience is a basic feature of the universe that cannot be reduced to purely physical processes. Matter might have both physical and experiential properties, with complex arrangements of matter giving rise to complex forms of experience. This panpsychist perspective would make consciousness universal while explaining why it seems irreducible to purely physical description. But panpsychism faces its own mysteries. How do simple conscious elements combine into unified conscious experiences? Why does the consciousness associated with your brain feel unified and coherent rather than like a collection of separate micro-experiences? The combination problem in consciousness studies parallels the measurement problem in quantum mechanics. Both involve the transition from multiple possibilities to single definite experiences. The relationship between consciousness and cosmology becomes even more puzzling when we consider the possibility that consciousness might influence physical reality through quantum mechanics. Some interpretations suggest that conscious observation is necessary to collapse quantum superpositions into definite states. If true, this would make consciousness an active participant in creating reality rather than a passive observer of it. The participatory universe hypothesis, proposed by physicist John Wheeler, suggests that observation doesn't just reveal pre-existing reality, but actually participates in creating it. In this view, the universe's properties are not fixed until they're observed, meaning that conscious beings play a fundamental role in determining the nature of reality itself. This would make the universe's ability to produce conscious observers not just remarkable but necessary for its own existence. But this leads to paradoxes about the early universe. If consciousness is necessary to collapse quantum states, how did the universe evolve for billions of years before conscious observers emerged? Some theories propose that any measurement, conscious or not, can collapse quantum states. Others suggest that the universe existed in superposition until consciousness emerged, retroactively determining its earlier history. Still others propose that consciousness is fundamental and was present in some form from the beginning. The fine-tuning of the universe for consciousness becomes even more mysterious when we consider how many things had to go exactly right. The universe needed to last long enough for stars to form and create heavy elements. It needed to be neither too dense nor too sparse for galaxies to form. It needed stars that burned steadily for billions of years. It needed planets at the right distances from their stars. It needed just the right chemical elements in just the right proportions. But the fine-tuning goes deeper than these large-scale requirements. The fundamental constants of physics seem precisely calibrated to allow complexity and consciousness to emerge. Change the strength of the electromagnetic force slightly, and atoms wouldn't hold together. Change the strong nuclear force, and stars couldn't burn. Change the expansion rate of the universe, and either everything would collapse too quickly or expand too rapidly for structure formation. The list of apparent coincidences required for consciousness is staggering. The ratio of the electron mass to the proton mass must be just right for chemistry to work. The strength of gravity must be precisely balanced against the other forces. The amount of matter in the universe must be tuned to extraordinary precision to allow the formation of galaxies and stars. Each requirement seems to have been met with impossible accuracy. Some cosmologists estimate that the probability of a universe capable of supporting consciousness is less than 1 part in 10 circumflex. 10 circumflex 123, number so small that it's essentially zero. Yet here we are, conscious beings contemplating the universe that created us. This seems to require either extraordinary luck, multiple universes where every possibility is realized, or some form of design or purpose built into the fabric of reality itself. The anthropic principle offers one explanation. We observe a life-friendly universe because we couldn't exist in any other type. But this seems to exchange mystery for tautology. It's like explaining why all the fish we catch are capable of living in water. Of course they are, because those are the only fish we can catch. But this doesn't explain why there are any fish at all, or why the ocean exists, or why water has the properties necessary for life. The multiverse hypothesis offers a different perspective. If inflation is eternal and creates infinitely many pocket universes with different properties, then universes capable of supporting consciousness must exist somewhere, no matter how improbable they seem. We find ourselves in such a universe not because it was designed for us, but because it's the only type where beings like us could exist to observe it. But the multiverse hypothesis raises new questions about the nature of existence and probability. If every possible universe exists somewhere, what makes our observations special? Why should we expect to find ourselves in a typical conscious observer-permitting universe rather than one that's barely capable of supporting consciousness? The measure problem in cosmology, how to calculate probabilities in infinite sets, remains unsolved. Moreover, if the multiverse exists, it raises questions about the nature of scientific explanation itself. Science traditionally works by finding simple, elegant laws that explain complex phenomena, but the multiverse seems to explain fine-tuning by asserting that everything possible happens somewhere. This makes every observation equally probable and seems to abandon the search for unique predictive theories in favor of pure anthropic reasoning. The relationship between simplicity and truth presents another deep mystery in cosmology. Why should the universe be governed by elegant mathematical laws? Why should simple equations describe complex phenomena? The fact that we can write down the laws of physics on a single page, while those laws give rise to all the complexity we observe, seems almost miraculous. Yet even our simplest theories contain mysteries. General relativity describes gravity as the curvature of space-time, but what is space-time made of? Quantum mechanics describes matter and energy as excitations of quantum fields, but what are quantum fields? Quantum field theory treats particles as localized excitations in underlying fields that extend throughout space. But this picture raises new questions about the nature of locality and the relationship between fields and the space they occupy. The standard model of particle physics, despite its extraordinary success, contains numerous arbitrary parameters that must be measured experimentally rather than derived from first principles. The masses of the fundamental particles, the strengths of the fundamental forces, and the details of how particles interact all seem to be free parameters that could, in principle, have any values. Why do they have the specific values we observe? Some theories attempt to reduce this arbitrariness by showing that apparently independent parameters are actually related. Supersymmetry, for example, proposes a symmetry between matter particles and force particles that would reduce the number of free parameters in the standard model. But experiments at the Large Hadron Collider have found no evidence for supersymmetry at the energy scales where it was expected to appear. The failure to find supersymmetry is part of a broader puzzle about new physics beyond the standard model. For decades, physicists have expected that higher energy experiments would reveal new particles and forces that would solve the standard model's problems and point toward a more complete theory. But despite building increasingly powerful accelerators, we found only the particles the standard model predicted. This drought of new discoveries has led some physicists to wonder whether we're approaching the limits of what particle accelerators can teach us about fundamental physics. The energies required to probe the next layer of reality might be beyond what we can achieve with any conceivable technology. We might be entering an era where theoretical physics must proceed without direct experimental guidance. But the universe itself provides laboratories for testing physics at energies far beyond what we can achieve on Earth. Cosmic ray particles arrive at Earth with energies millions of times higher than anything produced in particle accelerators. Neutron stars create conditions of density and magnetic field strength that cannot be replicated in laboratories. Black holes probe the nature of gravity in regimes where quantum effects become important. The study of cosmic phenomena has already revealed new physics that couldn't be discovered any other way. Dark matter was discovered through its gravitational effects on galaxies. Dark energy was found by observing distant supernovae. Gravitational waves were first detected from merging black holes. The universe is constantly performing experiments that test the limits of our physical theories. Yet, many of the universe's most extreme phenomena remain mysterious. Gamma-ray bursts, most powerful explosions in the universe, release more energy in seconds than the sun will produce in its entire lifetime. We think they're caused by the collapse of massive stars or the merger of neutron stars, but the details of how they produce such enormous energies remain unclear. Fast radio bursts, minus brief, intense pulses of radio waves from distant galaxies, were only discovered in 2007, and their origin remains completely unknown. These bursts release as much energy in milliseconds as the sun produces in days, but they come from sources too distant to study in detail. They might be caused by magnetars, black holes, or exotic physics we haven't imagined yet. The cosmic ray spectrum, the distribution of energies among particles arriving from space, shows features that don't match our current understanding of particle acceleration in cosmic environments. The highest energy cosmic rays carry energies that seem impossible to produce in any known astrophysical process. They might come from the decay of exotic particles left over from the early universe, or from acceleration processes involving physics beyond the standard model. Neutrino astronomy has opened a new window on the universe, but it has also revealed new mysteries. High-energy neutrinos detected by the IceCube Observatory don't match expectations based on known sources of cosmic rays. They might come from hidden sources of particle acceleration, or from the interaction of cosmic rays with dark matter, or from physics we haven't discovered yet. The cosmic microwave background radiation, the afterglow of the Big Bang, contains tiny temperature fluctuations that seed the formation of all cosmic structure. But these fluctuations show unexpected patterns that don't match the predictions of simple inflation models. There are hints of large-scale asymmetries, anomalous cold spots, and correlations that shouldn't exist if the early universe was perfectly homogeneous and isotropic. These CMB anomalies might be statistical flukes, instrumental effects, or signs of new physics. They could indicate that the universe has a preferred direction, that it underwent more complex evolution than simple models suggest, or that it's part of a larger multiverse structure that affects the properties of our observable region. Upcoming observations with more sensitive instruments might resolve these mysteries or deepen them further. The nature of cosmic inflation itself remains mysterious despite its success in explaining the universe's large-scale properties. Inflation requires a scalar field, Morno, that drives exponential expansion in the early universe. But we don't know what this field is, why it has the properties it does, or why inflation started and stopped when it did. Different inflation models make different predictions about the signatures they would leave in the cosmic microwave background. Some predict gravitational waves that would create distinctive polarization patterns in the CMB. Others predict non-Gaussian fluctuations or specific relationships between temperature and polarization fluctuations. Future observations might distinguish between these models and reveal the specific mechanism that drove inflation. But inflation might not be the complete story of the early universe. Some theories propose alternatives like echobarotic models, where our universe emerged from the collision of higher dimensional branes, or cyclic models, where the universe undergoes endless cycles of expansion and contraction. These alternatives make different predictions about primordial gravitational waves and other observational signatures. The very beginning of the universe, the first moment, if such a moment existed, remains completely mysterious. The Big Bang theory describes the universe's evolution from a hot, dense initial state, but it says nothing about what came before or what caused the expansion to begin. The initial singularity, where density and temperature become infinite, represents the breakdown of our physical theories rather than a description of actual conditions. Quantum gravity effects almost certainly become important at the Planck scale, where the universe would have been smaller than 10 circumflex 35 meters across. At this scale, the classical notion of space-time itself might break down, replaced by something more fundamental that we don't yet understand. Space and time might emerge from more basic entities, like quantum information or abstract mathematical structures. Some theories propose that the Big Bang wasn't the beginning of time, but rather a phase transition in an eternal universe. In these models, time extends infinitely into the past, with our Big Bang representing just one event in an endless sequence of cosmic cycles or phase transitions. This would eliminate the problem of what came before the beginning, but it would raise new questions about the nature of infinity and eternal processes. The problem of quantum gravity unifying general relativity with quantum mechanics represents perhaps the deepest challenge in fundamental physics. These two theories make fundamentally different assumptions about the nature of reality. General relativity treats spacetime as a smooth, continuous field that can be curved and stretched. Quantum mechanics treats everything as discrete, quantized, and probabilistic. String theory attempts to resolve this conflict by treating both matter and spacetime as emergent phenomena arising from more fundamental string vibrations. In string theory, particles are vibrational modes of tiny strings, and spacetime itself emerges from the collective behavior of these strings. But string theory requires extra dimensions and has so far made no unique testable predictions about our four-dimensional world. Loop quantum gravity takes a different approach, quantizing spacetime itself. In this theory, space is made of discrete, indivisible units connected by quantum links. Time emerges from the evolution of these quantum networks. The theory predicts that black hole singularities are replaced by quantum bounces, and that the Big Bang might have been a quantum rebound from a previous collapsing universe. Other approaches to quantum gravity include causal set theory, asymptotic safety, and emergent gravity models. Each makes different assumptions about the fundamental nature of space, time, and matter. The diversity of approaches reflects our deep uncertainty about how to reconcile quantum mechanics with general relativity. The measurement problem in quantum mechanics becomes even more puzzling when applied to the universe as a whole. Quantum cosmology attempts to describe the entire universe as a quantum system, but this raises questions about who or what measures the universe's quantum state. If the universe is all that exists, there's no external observer to collapse its wave function or select which branch of reality we experience. Some interpretations of quantum cosmology propose that consciousness is necessary to select which branch of the universal wave function becomes real. In this view, the universe exists in superposition until conscious observers evolve, at which point our observations retroactively determine the universe's history. This would make consciousness fundamental to the existence of definite reality. But this leads to paradoxes about self-consistency and causation. How can conscious beings evolve in a universe that doesn't have definite properties until consciousness emerges? How can we retroactively determine our own causal history? The relationship between consciousness, quantum mechanics, and cosmology remains one of the deepest puzzles in science. The nature of time in quantum gravity presents additional mysteries. In general relativity, time is just another dimension of space-time, relative to the observer and affected by gravity and motion. But quantum mechanics seems to require a universal time parameter to describe how quantum states evolve. Reconciling these different concepts of time is one of the major challenges in developing a theory of quantum gravity. Some approaches suggest that time itself might be emergent rather than fundamental. Just as temperature emerges from the collective motion of molecules without being a fundamental property of individual atoms, time might emerge from more basic quantum processes without being fundamental to reality itself. In this view, our experience of temporal flow would be a macroscopic approximation to underlying atemporal quantum relationships. The arrow of time, mind, the fact that we remember the past but not the future, becomes even more mysterious in this context. If time is emergent, why does it have a preferred direction? Why doesn't the emergent time run backward, making us remember the future and be uncertain about the past? The second law of thermodynamics provides a partial answer, but it's not clear why the universe began in a low-entropy state that allows thermodynamic time's arrow to emerge. These deep questions about time, consciousness, and reality bring us full circle to where we began, the recognition that the more we learn about the universe, the more mysterious it becomes. Each discovery reveals new depths of complexity and beauty that we never suspected. Each answer opens new questions that challenge our most basic assumptions about the nature of existence. We live in an extraordinary time for cosmology. We can observe the cosmic microwave background, detect gravitational waves, image black holes, and map dark matter across billions of light-years. We can probe the quantum realm with unprecedented precision and simulate the evolution of cosmic structure on supercomputers. Yet these remarkable achievements only highlight how much we still don't know. The universe remains fundamentally mysterious, filled with phenomena we can barely imagine and governed by principles we're only beginning to understand. Dark matter and dark energy dominate reality, yet we don't know what they are. Consciousness emerges from matter, yet we can't explain how. Quantum mechanics governs everything, yet we can't agree on what it means. Time flows forward, yet we don't know why. These mysteries aren't obstacles to be overcome, but invitations to wonder, reasons to feel awe at the extraordinary complexity and beauty of the cosmos in which we live. They remind us that science is not about achieving final answers, but about the ongoing refinement of our questions, the endless deepening of our appreciation for reality's richness and strangeness. As conscious beings made of star stuff, we represent the universe's attempt to understand itself. Every question we ask is the cosmos questioning its own nature. Every moment of wonder we experience is matter and energy organized in such a way that it can appreciate its own extraordinary existence. We are not separate from the mysteries we study, mere expressions of them, patterns of complexity that emerge from the same quantum fields and cosmic processes that govern everything else. This perspective doesn't diminish the mystery mystake. It reveals how much more mysterious and wonderful reality is than we ever imagined. We are not just observers of the cosmic story, but characters in it, participants in the universe's ongoing evolution toward greater complexity, beauty, and self-awareness. Until next time, this is your sleepy scientist, reminding you that in a universe full of unknowns, the greatest mystery of all is that we're here to appreciate the mystery. Sleep well, fellow cosmic wanderers, and dream of the infinite wonders yet to be discovered.